we will be showcasing Photon Engineering's FRED software platform. During today's webinar, you'll learn virtual prototyping of an optical setup for a phase shifting interferometer designed by OptoSigma to analyze interferometer performance. I would like to introduce you to our presenter, Tom Davies. He's the COO of CBS Europe. Tom has over 15 years of experience using and providing training in a range of optical engineering and photonics packages for the design of optical systems and photonics components. OptoSigma and CBS are working very closely together in promoting the FRED software platform to better support our customers. We will be recording this webinar and it will be available in a couple of days. We'll answer all of your questions at the end of the webinar. Please submit your questions using the Q&A button located on your Zoom toolbar. For those of you just joining us, welcome. And once again, I would like to introduce you to Tom Davies. He's the COO of CBS. Tom, please go ahead and begin your presentation. Thank you.
Thank you, Cindy.
You're welcome.
So I hope you can all see my screen. So my name is Tom Davies. I work for CBS, and we're a company that's been around since 2006. And we've been involved with providing technical support, training, and consulting services using FRED since 2009. We're headquartered in Canada, but we also have a branch office in Tokyo and Dublin to support the Asian and European market. So first of all, for those of you who don't know so well what FRED is, let me just give you a very brief introduction before I give you a live demo. So FRED is a comprehensive optomechanical systems analysis tool. It is a product from Photon Engineering, which is a company located in Tucson, Arizona. And it was first released in March 2001. So version 1 was 20 years ago. And it's used for virtual prototyping, stray light analysis, optical mechanical systems debugging, tolerance, fabrication, and testing. And it uses by default non-sequential ray tracing with an option for sequential ray tracing for classical optical design as well. So a couple of very simple use cases: stray light analysis in an imaging system, analyzing scatter and ghosting problems, creating artifacts on the image plane or detector, and also for non-imaging illumination systems as well. Quite simply, we like to say that FRED can be used in virtually every step of the R&D process, from the initial proof of concept through the initial designs, full analysis of the virtual prototype optomechanical system, and then tolerancing, debugging any issues with any sort of prototype, and then finally getting it ready for manufacture by integrating with vendor catalogs for suitability for manufacturing. So that was just a brief introduction to FRED. In regards to what I'm showing today, we're going to talk about using FRED to virtual prototype a phase shifting interferometer that was designed by OptoSigma. So here we're going to use FRED to virtual prototype this whole system on the optical bench, which is built using commercial off-the-shelf components, using, for example, the OptoSigma optical cage components that just plug in on the optical bench, and also things like the nano stage that moves the reference mirror position of the interferometer. So just very briefly, this model is created with a variety of different parts, but two things worth highlighting are the optical cage. Just really makes it easy just to plug and play, and this is a single, this can be just added in as a single CAD file, and very simply to virtual prototype this. And then also, this is a phase shifting interferometer where we need to shift the reference mirror by steps of 1/8 of a wavelength. And if we're using a helium neon wavelength, then we need a nanostage that will step it in around 80 nanometers per step. So we need to make sure that we have a precision motorized stage. And OptoSigma's model here does that very nicely, very easily, which actually has a resolution of 1 nanometer and a positional repeatability of 2. So these are parts of the system that we'll be modeling. Now, before we virtual prototype this system, we need to make sure that the software that we're going to use, and there's a variety of different optical engineering software out there, of which Phred is just one. But there are two requirements that are absolutely essential for virtual prototyping a system of this size. The first one is that because this is an interferometer, if we want to do any sort of simulations or calculations or analyses, we need to make sure we're using a software that can accurately simulate the propagation of the coherent beam and calculate the interference between the two paths of the interferometer. And not all optical engineering softwares can model coherent beams inherently. So that would be the first checkpoint to note. And the second thing is really depending on the system you're using. In this case, we have a large system with many optics and mechanical parts in a nonlinear fashion. It's very much a collection of parts located 3D in space. So we need to make sure that the software using can handle a large optical system like this in a CAD-like interface. Again, there are some optical software out there that would just list all of the surfaces in the model, mechanical and optical combined, in just one big linear list. And that would be a real pain to manage. And thankfully, Phred answers both of these requirements. Specifically for the coherent propagation, Phred uses a method called complex ray tracing, which is quite a nice technique where it uses the built-in ray trace engine to propagate effectively Gaussian beams, tiny Gaussian beams, the sum of which gives us an understanding of the overall field. And the nice thing about this method is that it can do this in an inherently non-sequential manner. So if beams split off or impinge on the aperture of an optic, that's handled inherently. And secondly, there's no extra step required to simulate any interference or diffraction effects. That's all built into the algorithm. So from the user's point of view, it's just a simple click the button and you get the results you need. And then addressing the second requirement, the CAD-like interface. So this is a picture of the Phred user interface. And you can see here that Phred uses a CAD-like tree on the left side to manage both the mechanical and optical parts of the model. And you can imagine this is essential when we're dealing with hundreds or thousands or hundreds of thousands of individual pieces. They could be arranged in hierarchical subassemblies and subassemblies inside subassemblies, and can be organized in a way that makes sense to you. And I'll show you in the live demo how I've done that. The nice thing about Phred is that it has a built-in library of OptoSigma parts. And any of the mechanical parts that you plan to use can be imported from a CAD file, a STEP, IGES, OBJ, STL file type, which can be downloaded from, in this case, the OptoSigma website for the part that you're interested in putting into your virtual prototype. So this is a phase shifting interferometer. And just a brief summary of what is actually happening in the calculation. Here on the top right, we have just a schematic of the optics without removing the mechanical parts, just so we understand what's going on. We have a laser diode source, which is helium neon in this case, and the comes through a beam expander and then a beam splitter, creating two paths. One path goes to the reference mirror driven by a nanostage. This is just a flat mirror. And then we have the sample mirror on the other path. Now, this is the whole purpose of the phase shifting interferometer, is to analyze the surface profile of the sample mirror. Essentially, through a series of calculations, we can understand the unknown surface profile. And that's the demonstration that I'll be doing in just a few minutes. So after reflecting off the mirrors, the beams come back, combine, and end up on our image sensor. So what we need to do to actually get this information of the surface of the sample is do the calculation 4 times. So we need to place the reference mirror in 4 different positions of lambda over 8. It's lambda over 8 because we need to change the path length by lambda over 4. So an eighth difference on each path, each half of the journey. And then we need to calculate the irradiance, the fringe pattern for these 4 positions, combine them in such a way that we understand the phase of the beam. And from this information, we can calculate the sag or the surface profile of the unknown sample. So to do this in a software, we have 2 steps. And because this is multiple calculations that combine, it makes sense to automate this as much as possible. And Phred has a nice built-in scripting language, which is really simple to get started and powerful, and allows you to automatically step through the positions of the reference mirror, do the ray trace, calculate the interferogram 4 times and save the data into this Phred terminology, this analysis result node, and then combine it to create the wrapped phase found from the simple difference and then the arctan. Once we have the wrapped phase, we actually need to unwrap it, allowing us to understand the sag of the surface. The unwrapped phase is can be a challenging method, and there is a huge collection of research papers about unwrapping phase. In this simple example, we took a reference paper from Heratz from 2002 that seems to work quite well, and we are able to change the unwrapped phase here into the wrapped phase into the unwrapped phase, allowing us to understand the surface profile. So that's what we're planning to do. Let me switch over to Phred. So now we're looking at the Phred user interface. This is the model that we've created from a series of CAD files. And you can see here that I've actually got the ray trace. I've got a simple laser beam. So if I just bring it to the top view, you can see this is the optical bench setup. If I expand the geometry folder on the left side, I've organized everything into mechanics and optics. And if I just right click on the optics and isolate, I just see, very similar to what I showed you a couple of slides ago, this is the optical path of the interferometer. It's just in this case, we want to include all of the pieces so that we can understand if we're going to impinge on any of the hardware, creating scatter effects, things like that. That's the essence of virtual prototyping. And you can see here, this is made up of quite a few different parts. If I just expand each sub-assemblies, you can see there's a whole different parts for each component that has been imported from CAD files provided by OptiSigma. So what we have here is we currently have a sample surface, and it's actually a plane surface, and it's just sitting right at the right-hand side here on the right-hand side of the model. And what we're going to do is create an unknown profile and then analyze it. So we start with a flat surface, and then we use what's called a modifier surface. And you can see here, I've expanded out underneath the term sag surface, a collection of different surface types that I have, which I can quickly add to the surface to mutate it and modify it in a way. And for this simple example, we're going to use what's called the freeform surface type. Quite simply, it is a bicubic mesh where a series of random perturbation points that we just generated randomly and added to the surface. So this is the random profile of the surface that we'll be analyzing. But you can see here, I can line up a whole series of different surface types and quickly flick through them, analyzing the different scenarios. And that's simply just by editing a setting on the flat surface directly, pointing it to the modifier surface. So because this this requires a series of 4 calculations, I wrote a script to do this. And scripts can be housed with the Phred file. And I'll just briefly show you what it looks like. I won't try and explain every line of the code, but I just want to point out that it is a version of Visual Basic. So if you have that experience, very simple. And quite simply, all we're doing here in this main loop is 4 times moving the reference mirror position, doing the ray trace, and calculating the irradiance. And then we're just storing the irradiance data and then combining them to create the unwrapped phase, which I'll show in just a second. To run the script, in this case on my laptop for this presentation, takes about 30 or 40 seconds in total. Obviously, if you had a more powerful desktop, it would take much faster. So we just have to wait patiently for this. But you can see here, I wrote some of my own reporting to this output window at the bottom of Phred, telling us we've calculated the interferogram for the starting position, quarter wave, half wave, and we need to do one more for 3/4 wave. And then it will combine them and create the unwrapped phase. And after the script is finished, I'll show you where it's housed and we can look at the data. But the nice thing about the scripting language is that we can automate any of these analyses, including swapping parts out, playing around with different coatings, or worrying about mirror misalignment. We can automate anything like this in the scripting language. That's what makes Phred a very useful tool for virtual prototyping. So the results of this calculation are stored in the analysis results folder. And you can see here, I've got 4 irradiance calculations, and then one called the wrapped phase. So if I double click on one of these irradiants, this is actually the interferogram for this perturbated surface. And we have 3 others that are very similar to that. I'll just show you one more. I won't show you all 4, but you can see how it's going to be slightly different each time. And then that data is calculated and combined in the script to create what's called the wrapped phase of the difference between the flat surface and the perturbated surface. So here we have an interesting result. This is the wrapped phase, and this circular aperture is the laser beam footprint that reaches the surface. So we can understand immediately that the laser beam reaches about ±3 millimeters in diameter. And well, radius. And then we can see, if I drag the mouse over, you can see on the right side that there's certainly, this is unwrapped phase. You can, sorry, this is wrapped phase, and you can see the jumps from -pi to +pi. So the next step is to unwrap this, and then we can actually get a understanding of the surface profile. So if I go back to my Phred model, and I've got a separate script to run to actually take that data and unwrap it for us, which is actually can be quite a challenging thing mathematically. So in this example, I just separated them into 2 scripts. Of course, it could be combined in just one simple push button, get the whole result at the end. Again, this takes about 30 seconds to do what it needs to do in terms of the unwrapping, and then I'll be able to show you the sag of the surface profile. And again, we're going to get the results stored in the analysis results window on the left side. Okay, so I see from my little note that it's done. And I can see here, these are, first of all, let's check the unwrapped phase. So this is the unwrapped version of the wrapped phase we just showed briefly. And you can see here there's no discontinuous jumps in the phase profile. So that looks good to me. And then let's skip straight to the surface sag. So this is the key calculation that we want. The whole purpose of the interferometer is to provide this type of result. And you can see here, the units are in microns. So this is the surface sag, in other words, the deviation from a flat surface based on this perturbation. And you can see here that we're ranging from 0 to about half a micron, so 500 nanometers. And you can see here that underneath this laser beam footprint, we can actually understand the surface profile. And this is the whole purpose of this phase shifting interferometer. So if you're using Phred, you'll be able to check that the system you want to design has been set up correctly, check that you've got a large enough footprint, or if you need to worry about how to scan across the surface, or if there's any issues with any sort of misalignment or very minor rotations in the stages. Anything like that can be prototyped along these lines using the software, either manually using the user interface and clicking the calculation buttons, or as I showed you, just by writing a script to automate things and giving you the calculation in the simplest way possible. And as I said, in this example, I won't do another example, it just takes a few minutes, but if I wanted to then play around with the freeform surface or swap it out to a Zernike profile, very simply, I just go back to the sample. So this is the actual surface settings of the sample. And then I would go to the modifiers tab and just choose my other profile. So I can switch to the Zernike, click OK, and then run the calculation again and see that surface profile. So very smooth way to play around with the different scenarios in the calculation. And again, once you're happy with the setup, then you know what parts you need to use, where to put them, and you can go ahead and actually build this prototype in your lab. And that's the whole essence of virtual prototyping. I should also point out, if you ever wanted to play around with the source types, just one final thing to mention. In this simple example, obviously we have this laser housing here. But essentially, I just have the optical source right at the output, and I've just defined a simple Gaussian beam source of 1/e squared width of 1.75 millimeters. And of course, this could be changed depending on what source type you want to play with. And again, that might be an option you want to optimize. This is a simple Gaussian beam, but also we could also actually switch to using different source types, such as the laser diode beam or an M² laser beam, meaning that we actually put in an M² parameter as well. Some laser diodes have those parameters that you need to take into account to understand how the beam expands as it propagates through the system. So you have all of this flexibility as well in regards to the source. And then one final thing is, here in this simple example, we have all the optics are perfectly transmitting or reflecting, depending on whether they're mirrors or lenses. But of course, that's the ideal unrealistic case. If you needed to account for minority reflection components from the lenses or small level of scatter from the mirrors, effects like that can also be handled by modifying the coatings put on the lenses and the scatter models that would be relevant for the mirrors or the lens surfaces themselves, basically simulating the small amount of scatter due to surface roughness from polished optics, for example. That can all be included, and you can see how the the interferograms start to degrade. And so you understand the limits of how polished the optics need to be and so on. Again, all of the things you need to check beforehand before you start building this system is something that you can do in this type of software. So just one final slide and then we can wrap up. I just want to say thank you. My name is Tom Davies, COO of CBS Europe, and please get in touch if you have any questions or want to discuss any details. And I'd just like to thank Axel Haunholter from Optisigma for helping set up this model, and also Ryan Irvin from Photon Engineering, who helped with the script to unwrap the phase, which was more challenging than I thought it would be when I first started out on this project. So thank you, and please get in touch.
Thank you very much for your presentation, Tom. It was fantastic. I'd like to remind everybody that we do have a Q&A button on the Zoom toolbar, so please go ahead and ask any questions you have for Tom to answer, and we'll go ahead and start the Q&A session. So we do have one question so far. The question is, which surfaces are usually evaluated with this setup? Is that common practice for free-form surfaces?
It is. Essentially, you often about manufacturing problems. So you might think that the surface is perfectly flat, but if you want to actually evaluate that, you would use this type of system to see if it is perfectly flat, see what the perturbations are. So yes, a free-form surface to represent the perturbations in manufacturing. Also, another typical surface type is a Zernike surface, again providing perturbations to the perfectly desired manufactured surface profile.
Great, thank you. We have several questions coming in. The next question is, are the rays drawn showing all the waste and divergence rays of the beamlets, or are they showing just the optical axis of each beamlet?
Okay, that's a good question. So when I first shared my screen and showed the Phred window, I showed the laser beam propagating through the system. That doesn't represent the full waste of the actual laser beam. That's just what we call the axis rays of every Gaussian beamlet, of which the coherent sum creates the optical beam. So the only way to really truly understand the beam footprint going through the system is to calculate the irradiance at the places you need. So it can be slightly misleading in that respect, but it's very useful just to see that the beam, to draw the axis rays and just see where it goes, the approximate width, and just to check if we're getting close to the apertures and starting to impinge on the hardware. But yeah, it's not the true beam size.
Thank you. The next question is, are there limits for laser sources that can be simulated with Phred?
I showed you briefly the source types. We have the standard Gaussian beam, the fundamental Gaussian beam source type. And then we have other source types for highly divergent laser beams, including the ability to set an m² parameter. Beyond that, it would have to be something customized, which you can do. So for example, a coherent point source, coherent plane wave, no problems. I guess the only limitation, or where it starts to become a little bit complicated, is if you need to start worrying about finite coherence lengths, because in Phred and some other optical engineering software, the assumption is the beam is fully coherent for the whole simulation. So if you need to start worrying about how it starts to lose its coherence, that becomes a more tricky calculation. It's not a fundamental limit, but it's not something that's built into the calculation. So I would say the one thing to be careful with is if you need to worry about finite coherent lengths.
Thank you. Next question is, can you import real surface data to use for your sample surface? What is the best way to do this?
Again, a very good question. It depends on the data you have. If you have a measurement data in a grid of numerical values, we could use that biqubit mesh surface I showed the interface for. You can just, if that's a text file, as long as it's in the Fred's readable format, which is very simple, you can import it directly into the surface from the text file. If you have data in a different format, it might make more sense to match the profile to a polynomial or something like that, and that can be done outside Fred or inside Fred, and then use that polynomial function for the surface, or breaking down the data into a collection of Zernike coefficients. So it depends on the data you have, but certainly the most common one that I'm thinking of right now is the numerical data imported into the mesh, and that will create the SAG profile.
Okay, thank you. Next question. What is the particular advantage of Fred software against competitors in this particular example?
In this particular example, I did highlight this at the start. Two things, and not unique by any means, but two things that Fred does very well, which other softwares might not, is it can handle large files in a CAD-like manner. So even if you had a system with hundreds of thousands of surfaces, it's still relatively easy to manage in the tree. Everything is in its right folder, and you can manage it quite well, including the fact that you can isolate different pieces, you can drag and drop optical properties to the pieces you need. It's very nice to manage large systems. And then the other feature, which again, not unique to Fred, but certainly not available in some other of similar software, is the ability to calculate the coherent beam propagating through the system. If you need to design in a difframeter or worried about diffraction effects, either aperture diffraction or something else, you have to be able to coherently propagate the beam, understand the wavefront, the phase, the vector field, and be able to calculate interference. It can't be done if the software is, it can't be done well if the software is only managing to propagate incoherent into incoherent rays. So that's a key thing to make sure that you need for this type of system.
Great, thank you. We have several more questions. The next question is, does the UI support multiple screens, for example, showing results, scripts, and the design tab on different monitors?
I'm not 100% sure about different monitors because I've never used a system with two monitors. I'm very simple. I only have the one screen in front of me, but certainly I showed you the big window with the 3D view of the tree and the output plane. I can minimize those and make them my own size, make them my desired size, and put them side by side with the analysis window. Certainly. I'm just slightly uncertain if I can then drag it over to a second monitor. I'm not 100% sure that's the case, but certainly I can have a vision where I can see the analysis result and the 3D view side by side. I can tell you that. I'm just not sure if it can be dragged beyond the boundaries of the Fred UI.
Okay, thank you. Next question, what is the particular advantage of Fred, or I'm sorry, we already answered that one. The next question, does the UI support, oh, sorry. That one's answered.
Okay.
We're getting questions in two areas, so. How do you decide the sampling of the source and analysis surface?
Good question. And this is an interesting way how Fred does the coherent calculation. I used a ray grid of that laser source of just 21 rays across each axis, totaling about, I don't know, 300 and something rays. And when you're modeling coherent beams, when you're modeling incoherent beams, the rule is more rays, better accuracy. That's not so much the case in this algorithm. All you've got to do is make sure that you have enough rays to spatially sample your source profile, so that if you plotted the laser beam source, it'd be a nice smooth Gaussian without any sort of ripples or strange artifacts. So typically you don't need that many rays for a coherent calculation. I did one of those ray trace calculations through this system took about 4 seconds on my computer, and I don't have a powerful computer for this presentation. If you had a modern desktop computer, it would take just 1 or 2 seconds. So it's really not a heavy, computationally intensive calculation. In regards to the analysis surface, that depends on the details of the situation. I used a grid for the interferogram calculations, I used a grid of 200 by 200 pixels, which is kind of where I start a calculation like this. If it's not enough, you have to plot it and say, you have to decide for yourself if you need to increase the resolution or not, or if you have unnecessary high resolution. It's a judgment call based on what you see when you calculate the irradiance, I think. But certainly in this case, I felt 200 by 200 was sufficient.
Okay, thank you. Next question, can you upload an experimentally measured surface for the optical surfaces?
Yes, it's very similar to the question we had a couple of minutes ago. Yes, ideally you have the data in a numerical grid, and that can be uploaded into the surface profile, that mesh surface I showed you. There's just a button where you can just upload the text file of data, and that's all you need to do. So yes.
Thank you. Next question, after tracing the initial source through an optical component, is there a way to know the new waist size and position, perhaps using ABCD methods?
I'm sure that you could do a similar calculation using ABCD matrix methods to calculate the beam propagation. But it's simpler just to put an analysis surface at the location you want to check the beam waist. So Fred has this concept of analysis surfaces, which are just calculation grids, and you place them where you need to. And then you do the ray trace, and when the rays reach that analysis surface, you can plot the irradiance and check the beam waist and all other parameters you might need to, including polarization, state, and things like that as well. So essentially, the method that Fred uses, called complex ray tracing, or it's also called Gaussian beam decomposition, is an alternative to ABCD. You wouldn't need to do anything else. You just need to tell Fred, I want to look at the beam waist at this location and calculate the irradiance for that plane.
Thank you. Next question, can Fred be used to model cavity modes and resonance?
Okay. Yes, but not very well, is the truthful answer. We have some examples where we've created a laser cavity and seen how the propagate the rays bouncing back and forth between the mirrors, and seeing how the beam evolves over time and resonates. But it's a time evolution calculation, and ray tracing generally doesn't have any time component. So you have to do something a little bit unusual in the fact that you have to control it. You have to write a custom script. And we have examples of this if this is something that you want to do and need some help with, where we calculate the beam evolution for each round trip and adjust any parameters such as the gain of the medium and things like that. So the answer is not very well. And certainly I'm talking about a cavity that's Riesemann size. We're not talking about any sort of semiconductor laser cavity. We're talking about a gas laser or something like that. So there are some limitations there, but I mean, if it's essential to your work, Fred can be used. It just takes a bit of work to get started, which is something we can help with.
Thank you. The next question is asking about the Fred file that you presented today. And I just want to add before I ask this question is that all of the OptoSigma optical components are available on our website. Next to that particular component, you can download the step files for that. We can also provide any files for you. The question is, can you provide the Fred file to take a closer look and play around in?
Yes. Please reach out to me directly and say you visited the webinar today, and you'd love a copy of the Fred file, and I'm happy to send it to you. Yeah, and as Cindy said, yeah, the all of the pieces of that system that you saw there were downloaded or provided by OptiSigma. So if we wanted to use that nanostage or the cage system, that's just available on the website. When you're browsing for the different parts of the OptiSigma website, you can just download it as a step file and read that into Fred and put it in the right position. And that's how the model was created.
Okay, great. Thank you. Somehow I lost the Q&A box. My mouse is a bit frozen.
Okay.
Hold on one second. Sorry about this.
No, sure. And I should say that if you reach out to me and ask for ask to share the Fred file comes with the scripts as well. So it has the script to do the 4 interferograms and the unwrapped phase, and the phase, and then also the script for unwrapping the phase as well. So that's all inside the model. The only issue is that this Fred file, because of all the CAD files, is about 100 megabytes. So I wouldn't be able to send it by email, but I'll be able to provide a link to download it.
Okay. The next question, will the scripts and or the Fred file from today's presentation be available for us to look at later? Oh, I'm sorry, that one's already.
Yeah, we've done that one, yeah.
Is the benefit of using Fred MPC, which can be used with GPU machines, better utilized when using larger models, many components, or larger array sets for greater sampling and more freedom surfaces, or both?
Yeah, it's a good question. So Fred MPC, which you might have noticed in my presentation, was the logo I used with the MPC superscript, is the highest version of Fred that does the GPU ray tracing. So to speed up the calculation, it can do the calculation on the GPU boards. So any NVIDIA GPU board can be used to speed up the calculation. And the speeds are very impressive. We say typically 100 times faster than a CPU ray trace, a multi-threaded CPU ray trace. But truly, it depends on the type of board you have, and you can stack up boards together. So we've done cases where we've seen 1,000 times faster. So obviously, it's really valuable if you are tracing billions of rays through large optical systems with many surfaces, and you're having to wait many hours just for the result. Some Fred users were waiting days for their calculation result. It's not so useful in this specific example because I'm only tracing about 400 rays. So the ray trace in this example took about 3 or 4 seconds. And when you use the GPU boards, there's an overhead at the start of about 10, 20 seconds, loading the model and the conditions onto the GPU board before speeding through the ray trace. So in this specific example, because of the small number of rays, it's not that valuable. But if you were doing any sort of stray light analysis using an incoherent beam through a different system perhaps, and you think it's going to take hours for the calculation, then MPC using the GPU ray tracing would just do it in minutes as opposed to hours or days. So in this specific example, no, but Fred MPC can be truly valuable if you're sitting waiting for the calculation result. So the rule of thumb is if you get into the habit of clicking run at the end of the day and hoping when you come in tomorrow morning that it's finished, if you're in that scenario, then MPC is probably truly valuable for you.
Thank you. Can Fred be used to model bulk fluorescence out of the box?
Okay. Yes. I'm laughing because I had a couple of similar questions recently from other meetings I had with potential Fred users. The answer is Fred doesn't do fluorescent very well, unfortunately. It can model fluorescence, but the user has to put in the hard work. There isn't a built-in function where you upload the emission spectrums and the excitation spectrums, and that's all you need to do. You actually have to use the scripting language to simplify it. To set it up for yourself, of which we have some examples, but I wouldn't say it's straight out of the box. It can be done. As with Fred, many things can be done. It can really flexible enough to do pretty much anything in terms of optical engineering. It's just some cases there isn't a toolbar button for it, and you have to customize a script to do it for you. But in many cases, if it's something as frequently requested by like modeling bulk fluorescence, chances are I've already written script that I can provide to help people with.
Thank you. Next question, is there a live link integration with CAD softwares like SolidWorks or AutoCAD?
No, that's perhaps one small demerit against Fred, is that there's no dynamic link to a CAD software. So what you have to do if you have designed the CAD in Fred, in a CAD file, you have to export it to one of the common shared file types, STEP, IGES, OBJ, STL, and import that into Fred and then assign the optical properties. So it takes a few extra steps than the dynamic link, but also gives you some flexibility in the fact that you could use your preferred CAD software as long as it can export the commonly used CAD file types.
Great, thank you. Does the presence of the CAD objects affect the speed of the trace?
Yes. Very generally speaking, in all ray tracing software, non-sequential ray tracing software, the calculation time depends on the number of surfaces or number of objects. So in non-sequential ray tracing, when a ray leaves a surface, the software has to calculate, which surface is it going to intersect with next? So it has to cycle through that whole list of surfaces and check to see if the ray is going to be propagated close to that surface. So you can imagine if that list is longer, that part of the calculation takes longer also. So the answer is yes. So typically if you have a CAD file with hundreds of thousands of parts or surfaces, it's often a good idea to minimize the whole system to remove the pieces of the CAD file which are totally irrelevant to the optical system if you're worried about calculation speed. In this example, I wanted to show you the full optical bench of the system, but truly I could have removed half of those CAD files, like the optical bench, the base, the handles on the side, the base underneath the camera. We're not going to worry about light hitting those objects. So in theory, if I was worried about speed, I could have made my file a bit more efficient. So the answer is yes.
Thank you. Next question, does OptoSigma provide any of the BRDF data or typical surface roughness data for their mechanical components? For example, a typical black anodized aluminum lens mount.
I don't know the answer to that.
Right.
That's a question for OptoSigma engineers. I can't answer that, but I can tell you that if you know those numbers, you can plug them into Fred and simulate the effects of these surface roughness and these scatters.
And to answer that question, we do have a lot of that data available. It depends on the parts, as far as if we need to sign an NDA or anything like that to provide that information. But please reach out to OptoSigma if you would like that data and it's not available. We could certainly work with you to provide whatever information you need. Next question, can Fred simulate Fresnel edge diffraction of the half plane?
Yes. That's built in inherently in the coherent beam propagation of the algorithm of Fred. So you can simulate diffraction of Fred, edge diffraction, aperture diffraction. Should be no problem.
Thank you. Next question. We only have a couple more left. Should Fred be more considered as an illumination software or optical design software?
It should not be considered as an optical design software in the true sense of optical design, meaning lens design. If your whole purpose is designing a lens prescription, I would recommend using another software. Where Fred becomes very valuable is the larger optical system. So any sort of stray light analysis, be it specular ghosting in a lens or scattering from housing around an imaging system, or illumination systems as well, non-imaging systems, or in this case, a laser system. That's where Fred is really very valuable. But I'd say no to optical design yes to illumination, but also I'd say Fred's best reputation is probably stray light analysis in the aerospace industry. That's where a lot of users use Fred, especially in the US, where Fred has a larger user base, and photon engineering is much wider known than perhaps in Europe. But of course, illumination systems, coherent beam propagation for laser systems are key merits as well.
Great, thank you. And we just have one more question. The last question is, you mentioned prototyping. Is it possible to calculate thermal and mechanical influences in the setup?
Yes and no. There's no inherent way to model thermal changes. What you'd have to do is model the system at discrete temperature values. So at the room temperature, you could do the simulation, and then you would have to, through a script, work out the changes as you increase the temperature. And then you do a series of individual calculations and then try and get the understanding that way. So there's no dynamic way to import or set up the thermal changes of the lenses or mechanics and seeing that evolve. You have to do the hard work yourself, unfortunately.
Thank you. And thank you for answering all the questions. We had a lot of great questions today. I appreciate everybody taking their time to join us. If you have additional questions for Tom, you can reach him at his email address, tdavies, that's TDAVIES, @cbseu.com. Also, you can reach out to OptoSigma at sales@optosigma.com. We also did record this webinar. All attendees, and even the ones who didn't attend but signed up, will also receive a link to view the recording on demand in a few days. So I hope that you enjoyed the session and we answered all of your questions, and we look forward to the next one.